In this video, we're going to go over the derivative as the rate of change, which is the Chapter 1, Section 8 section. So what we're seeing here is I've derived derivative as a rate of change. So that's kind of a new term for us. I've mentioned it a couple of times, but we're used to what are the words for derivative. So you're used to calling a derivative something like f prime of x. You're used to calling it the slope. And now I want you to get used to calling it the rate of change. All right, so given that, we're going to talk about one particular rate of change, and that is the average rate of change. So the average rate of change over some function is calculated by this formula, which is just the equation for slope. So we need to define B's and A's. So we start out, so let me just slide this up a little bit. We're starting out looking at this function, and we're going to figure out the rate of change from 2 to 1. So let's just see if we can highlight this area. So I want to look, make it red, right in here. Okay, this is where we're focusing our attention. So to figure out the slope of that secant line, so I'm going to write that it's a secant line right here. To figure out the slope of the secant line, we just use our delta y over delta x, and we can see the slope of that secant line. It's called a secant line because it's touching, let me get rid of this, it's touching this line, this curve, and our curve is the x squared curve. That's our function, as indicated right here. So that secant line, which is right here, is hitting here and here, hitting two places. So it's an average rate of change, and it's the slope of a secant line, and we're getting a value of 3. Okay, so let's move down, and we're going to look at the bottom of this page. Now we still have a slope of a secant line, but look what's happened this time. We're moving from 1.1, that's our B, to 1, that's our A. Focus your attention right here. It is getting smaller and smaller, but I'm still talking about it as an average rate of change, and we are still looking at the slope of a secant line. Okay, let's move to the next page. So initially we had a value of about 3, and now we've moved down to a value of, let's see, where are we? Okay, let me go back. So let me see. Okay, on this next page, we are now really close. Now technically, we are still looking at a secant line, but they're so close, they are only 0.01 away from each other, so you can see that we're approaching a value of 2. So initially we had, let's look back, okay, on this page we can see that we have looked at our points, our A and our B, so let me just identify them for you. That's our B, that's our A. We see they're getting closer and closer. So initially when we were doing this problem, we had a slope of 3. Then we went to a slope of 2.1. Now they're even closer at a slope of 2.0. This is still a secant line, but notice that our interval is getting smaller and smaller and smaller. So in the limit, we have the instantaneous rate of change, and that is the slope of a tangent line. So if they're asking you to figure out the average rate of change, you're just doing change in y over change in x. If they ask you to figure out the instantaneous rate of change, that is the slope. So very critically important. When we talk about going from average rate of change to instantaneous, we are approaching doing a slope. So your slope is your instantaneous rate of change. So that's an important point to consider. Okay, on the last page of the notes, we start out saying, let's consider functions that describe the position of an object with respect to time. These might be functions that view distance versus time. Another way to think of a derivative is a rate of change, but what kind? I'm hoping you're saying instantaneous rate of change. So the derivative of a position function describes the rate at which a position changes. And the rate at which a position changes is velocity. So let's just think of that again. The rate at which a position changes is considered the velocity. So my previous statement is summarized right here. Then, going one more step, the rate at which velocity changes is acceleration. So your brain should be thinking physics, because this is all physics. So let's look at a problem. So if y equals st is a position function, and this is very important, then y prime is velocity, y prime prime is acceleration. So in English, the first derivative of a position function is velocity, and the derivative of velocity is acceleration. Okay, you have to memorize this, because if they give you a position function, they're just going to ask you for velocity and acceleration, and you have to know that the first derivative is velocity and the second derivative is acceleration. Now let's work through a problem. Okay, so here's the problem. Suppose a ball is thrown upward so that its height in feet is given by ht, so height, equals negative 16t squared plus 128t plus 5. And t is time in seconds. Okay, so if you have a function that compares height and time, that is a position function. You have got to recognize that. So that's a position function. Our first problem says find the velocity of the ball 2 seconds after it is thrown. Okay, before you can do anything with this, you have to ask yourself, what is this asking me? So, since we've pointed out that the h of t is a position function, finding the velocity is going to be finding the h prime of t. Finding the velocity of the ball 2 seconds after it's thrown is evaluating the h prime of t at 2. This is what you're doing. These problems are not difficult, but you have to understand what they're asking you to do. So since velocity is derivative, then h prime of t is negative 32t plus 128, and therefore you can evaluate it, and you see that your velocity is 64 feet per second. Units are hugely important here. Next question, find the time. So find the time when the velocity is negative 32 feet per second. So in this situation, you're going to set your velocity equal to negative 32 and solve for t. So be able to distinguish between question A and B. They tell you the velocity for B, and they want to know time. So what do we know velocity is? So velocity is going to be right here, negative 32t plus 128. So to answer the second question, you're going to set your h prime of t equal to the negative 32 and solve for t. So we're going to do more problems like this, but what you should notice is if you have negative velocity, what does that mean? That means that the ball is falling rather than rising. So what did this whole function look like? Well, look at our original equation, and what it's going to look like is a parabola. It starts at 5 feet, it comes up, it comes down. Clearly you can see that the velocity or the slope is positive. So where is it positive? So it looks to me like it is positive right in here. Okay, then it's 0 right here at the max, and then on the other side the velocity is negative because the slope is negative. So at this point in your calculus career, you're going to be doing a lot of analysis of physics equations. And this is a whole different way to think about it, and it's much easier. For your assignment at this point, you're going to do this classwork / homework in the textbook. So read. Now this says read and go through examples in 1.8. That does not mean skip them and go to the problems. First, work through the examples. It would not be a bad idea to do this in your notebook. Then, start looking at the problems. Do one at a time, from 1 to 15. They're odd. All the answers are in the back of the book. Check as you go.